Welcome back. In this video, we're going to talk more about polar bonds and compare them to nonpolar bonds and ionic bonds. And so just to remind you, in the first video, I talked about ionic compounds and what they looked like and how they had a large difference in electronegativity. And then in the second video, we talked about nonpolar covalent compounds and how those arise from when you have elements that have almost the same electronegativity, and so there's no partial charges. You got a sharing of electrons. And in this video, we're going to talk about polar covalent compounds. So let's take a look at our first example. So I have hydrofluoric acid here, also known as hydrogen fluoride. And if you take a look at hydrogen fluoride, just the formula is just HF, simply HF. So I'm going to do the same thing that I did in the first two videos, which is to write out just the actual atoms themselves. So I've got a hydrogen atom, right, just has one valence electron, so hydrogen, my one dot. Hydrogen, right, is located up here, first element right on the periodic table, upper left. And I will also draw a fluorine atom, so fluorine with its 1, 2, 3, 4, 5, 6, 7 valence electrons. And fluorine, right, is over here, group 7, so all the way on the right-hand side. And just like we did in the previous videos, right, if I want to know what type of bond I'm going to have between any two given atoms, I want to know what is their difference in electronegativity. How different are they? Is there a large difference in electronegativity? Is there a small difference in electronegativity? Or is there like no difference in electronegativity? And you might think at first glance, looking at these two elements, right, hydrogen and fluorine, if you just look at the periodic table, it looks like they're really far apart. And it looks like there might be a large difference in electronegativity. But what you want to keep in mind is that hydrogen really doesn't belong over here in group 1 in terms of its electronegativity and whether or not it's a metal or non-metal. All right, you want to remember that you have this sort of diagonal here that separates your metals and nonmetals, and everything to the left is a metal, and everything to the right is a nonmetal. Hydrogen's over in group 1 only because it has a single valence electron in its outermost shell, and because it tends to form +1 charges like all the other group 1 stuff, those alkali metals. But hydrogen itself is not an alkali metal. Where hydrogen belongs in terms of electronegativity is right here between boron and carbon, right? So the elements right here, if you don't have a periodic table out in front of you, that's boron, that's carbon. Hydrogen belongs between those two in terms of its electronegativity. So you really want to think about hydrogen as being somewhere over here, right? So it's kind of smack dab between boron and carbon in terms of electronegativity. So that means that I don't really have that large of a difference in electronegativity. It's just a few spots over, and if you looked up the values, you'd see that the values are not that different. There is a difference, but not that different, not a large difference. So what I'd say about hydrogen and fluorine here, right, is that there's a small difference in electronegativity. Right, so we're saying that I don't have a huge difference, so I'm not going to get an ionic compound. It's not that there's no difference, so I'm not going to get a nonpolar covalent compound. There's a small difference, which is going to give me a polar covalent compound. And let's take a look at what that's going to look like here. So fluorine, right, we've said before that fluorine is very electronegative, right? It's the most electronegative element. So it really wants, so I'll put really, it really wants electrons. It pulls very hard on electrons. Pulls very hard on electrons. Whereas if I go over to hydrogen, I can't really quite make such strong statements about it. Yeah, it's over on the right-hand side. Yeah, it's relatively electronegative, but it's not really electropositive. It's not that it has like no electronegativity. It has some. So it's not that it really wants electrons. It sort of wants electrons. It wants electrons. You know, it wants electrons, and it's going to pull a little. Right, it's going to pull a little on electrons. But it's just not as much as fluorine. And so since I don't have this huge difference in electronegativities, that means that I'm not going to see a transfer of electrons like we saw with the ionic compounds. We're going to see a sharing of electrons again. So this is another example, right? Because it's a covalent bond, this is going to be a sharing of electrons. And so instead of transferring the electron to the fluorine or to the hydrogen, they're going to end up sharing just like we saw with the nonpolar things. And so again, you can draw them buddied up, like again we showed in previous videos. So where I have now the fluorine hanging out real close to the hydrogen so that it looks like their outermost shells have filled, that they look like the nearest noble gas, right? Because, again, if you look at fluorine, now if you share electrons, right, if you have this covalent bond, so I'll put, here's my covalent bond. Right, if you have this covalent bond here, those two electrons, the blue one and the green one that are now being shared, if you have that covalent bond, fluorine now sort of looks like its nearest noble gas, like it has its octet, right? 1, 2, 3, 4, 5, 6, 7, 8 electrons. It looks like its nearest noble gas, which is neon. If you take a look at hydrogen, it also looks like its nearest noble gas, which is helium, which has 2 electrons, so it sort of filled its shell. Now, you'll notice it's not an octet, which is one of the reasons I'm not a huge fan of calling it the octet rule. I like the noble gas rule. It doesn't have an octet, but you don't have to have 8 to have your shells filled. You don't have to have 8 in order to look like the nearest noble gas. So these both fulfill the noble gas rule. So I'll put fulfill noble gas rule. And again, you'll see these sort of shared dots, but we can quickly switch to just drawing the line in between them like we did with other compounds, right, where we had covalently shared electrons here. So again, here's just your covalent bond. Now the big difference here between HF and like F2, like I showed in the last video, is in F2, right, we said that these... neither one of these fluorine atoms pulled electrons more than the other fluorine atom, right? Because they are the same element, they have the same electronegativity. So their electron clouds were pretty evenly distributed. Neither one was more electronegative than the other one. Now, if we look at HF, though, that's no longer the case, right? I have H and I have fluorine. And so now what we see here is that there is a winner and a loser in terms of the sharing, right? Again, it's not that fluorine is so much more electronegative it's going to steal an electron, but it is more electronegative than hydrogen. So that means we're going to see some electron density shift to the fluorine side. And we express that by drawing this arrow, which is called the dipole arrow. And it always goes towards the more electronegative element, right? So we know that fluorine is more electronegative than hydrogen. So it always goes towards the more electronegative atom. And what that causes is sort of an unequal sharing of electrons now. So if you imagine that looks relatively even, now the idea is that the fluorine sort of hogs those electrons and it's lopsided. So more of the electron density is on the fluorine side than the hydrogen side. And the consequence of this, right, if I have more electrons, which are negatively charged, if I have more of the electron density on the fluorine side, then the fluorine's going to start getting a little more negative. But not fully negative, because it didn't actually steal an electron, so it's not a full negative charge. It's just part of a charge. And so we see these deltas, these lowercase deltas that look kind of like an S that curls back on itself. That means that there's a partial charge there. It means it's partially negative. So let me write that. That means it's a partial negative. So a partial negative charge. It's not a whole negative charge, it's just a little bit of one. It's just a partial negative. And what you'll see is you'll see the same thing on the other side, right? So if the hydrogen had some of its electron densities taken away by the fluorine, that means that hydrogen is losing a little bit of electron density, so it's going to become a little positive. And so the hydrogen then now is partially positive. So we have a partial positive. Partial positive. And you notice when you draw these dipole arrows, right, that we see that there's like this little plus sign thing on the dipole arrow. That plus sign always hangs out next to the atom that is partially positive, and the arrow goes towards the atom that's more electronegative, or in other words, the atom's going to become partially negative. And so this is what sets up our polar covalent bond, the idea that we have this pole because we have a partially positive side and a partially negative side of that bond. We don't have an equal sharing of electrons, we have an unequal sharing of electrons. And in fact, I'll add that now and repeat it at the end, that in polar covalent compounds, you have an unequal sharing of electrons. Unequal sharing of electrons. And that's what gives rise to the polar covalent compounds. So let's take a look at some other representations here. So here's other representations of hydrofluoric acid. These top three, right, these, just as reminders, these are your F compounds. So fluorine, 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 fluorine. And again, you'll notice that in these, right, this electron density here, this is evenly distributed. Evenly distributed. Right, I don't have more electrons on one side of the molecule versus the other one. They're evenly distributed. But if you go to something like HF, right, so again, this is the hydrogen, this is the fluorine. Here, this is showing that the hydrogen is smaller than the fluorine. Fluorine's bigger than hydrogen. But here, for this HF, right, here's your H going over into the F side. Not that you can see the F red on red. It's not the greatest. So the F. What you'll see here, right, is that these are not evenly, right? These are unevenly shared. They're unevenly distributed. So unevenly distributed. These electrostatic potential maps, these rainbow-looking things, red means that something's becoming a little more negative. That's what red means on these electrostatic potential maps. And blue on these electrostatic potential maps means that something's becoming more positive. And so you can see if you calculate these, that the H does become a little bit more positive and the fluorine side becomes a little bit more negative. And so you set up, again, what's called the dipole. And again, I could draw the dipole arrow here and just add that on, where the dipole arrow shows that the electron's density is moving towards the fluorine, that more electrons are around the fluorine than they are the hydrogen, giving us this dipole. And so it's very different, right? So if I take a look at these, right, the top examples would be a nonpolar bond, a nonpolar covalent bond, where the bottom ones are polar covalent bonds, right? And that's the difference. It's all about how they share electrons. In both cases, you share electrons. In both cases, you have a line between the two atoms, but in nonpolar, they're of almost the same electronegativity or the same electronegativity, so you have an equal sharing. Versus with polar, they have a difference in electronegativity. So in our case, the H is more electronegative than the fluorine. Let me give you one more example. So water, right? Everyone's familiar with water, good old water. Again, here are my atoms. Let me erase that. So I've got my atoms. We've got an oxygen atom. 1, 2, 3, 4, 5, 6 for my oxygen atom. Looks like we have 2 hydrogens. So I've got 1 hydrogen, 2 hydrogens. Again, if I want to know what the Lewis structure of this looks like, I just need to kind of connect these dots here, right? Oxygen, because it has 2 unpaired electrons, wants 2 bonds. Each of these hydrogens wants 1 bond. So I know that I just need to kind of connect them, and then I'll have my new covalent bonds. But how do I determine how is it polar covalent or non-polar covalent? Again, right, it's all about electronegativity. So remember that H belongs right here between boron and carbon, whereas the oxygen is over here, right, fluorine, oxygen, oxygen's right here. And so again, what I see is a small difference in electronegativity. So a small difference in electronegativity, which is, again, what's going to drive, the type of bond that we have. All right, so again, I should think that, oh, okay, this is going to be a polar covalent bond. Polar covalent bond. And so again, we will have a sharing of electrons. This one's going to share here. This one's going to share here, giving us our water molecule. So here's what my water molecule should look like in the end. And now, since I think it's polar, that means that I need to put the dipoles on. I need to put those partial charges on. And to do that, you just look at an individual pair of atoms that are bonded to one another. So I'm not going to look at the whole molecule. I'm just going to look at each polar bond. So I've got one OH bond right here. I know that that's polar. And I need to ask myself, which one of those two elements is more polar? Is it the oxygen or is it the hydrogen? And again, since oxygen's further to the right and higher, or it's, in this case, it's just to the right, but you're right, the periodic trend is up and to the right. Since oxygen is more electronegative than hydrogen, it's more to the right than hydrogen is, I know that oxygen's more electronegative, which means it is going to get more of the electron density, so it should be the thing that's partially negative. So let me erase that. Here we go. So it should be the thing that's partially negative, right? Because it's kind of taking electrons from this hydrogen. It's taking some of that electron density. Again, if you want to see the dipole arrows, I could have written the dipole arrow like that, where I show that I draw the arrow towards the more electronegative element because that's the element that's going to pull on electrons. Now, I didn't look at the other OH bond, but it's going to be the same thing, right? It's an O and an H. The H is more electronegative, so I could imagine another dipole going towards that oxygen, and that means that the oxygen should be more electronegative and therefore have the partial negative charge on it, but I've already drawn that, so I just need to add the partial positive to my hydrogen. And then I've got my dipoles written on my water, all right, which must mean that water here is a polar molecule, right? This is a polar covalent molecule. These bonds are polar covalent, and this whole molecule is. And we'll talk later about distinguishing the difference between is a bond polar versus is a molecule as a whole polar, but we'll get into that later. I want to do one more example here with this much larger molecule here. And I actually need to add something for you all. This should be a carbon right here, just so you know. This is the organic chemist in me not drawing carbons when I should. That's a carbon. If I want to add all the partial charges, right, to this molecule, what this is really asking me is where are the polar bonds, right? Because that's where the partial charges go. So where are the polar covalent bonds? Where are the polar covalent bonds? So I'm going to go through this and I'm going to ask myself which one of these covalent bonds is polar and which of these covalent bonds is nonpolar. I don't need to worry about ionic compounds or any ionic bonds because I don't see any ions here. Nothing has a full charge, plus I see everything's connected by a line, and again, the lines mean that they're covalently bound. So like, for example, N and H, this NH out here, I need to ask myself, does nitrogen and hydrogen, do they have a small difference in electronegativity or a large difference in electronegativity? And if I look at hydrogen, right, again, hydrogen's right here in terms of electronegativity. Nitrogen is over here. I'll put carbon in here right next to it. And it looks like I've got an oxygen and I've got a chlorine. Let's put the chlorine down here, Cl. So there's my little periodic table up there. Since nitrogen and hydrogen do have a small difference in electronegativity, I'm going to say that this is a polar bond, and I'm going to use blue for polar. So polar bond here. And that includes the other NH, so that's a polar bond. I've got the CN bond next to it, carbon and nitrogen. They're right next to each other, but they do still have a difference in electronegativity. It is still a small difference in electronegativity. And I'll put that in here just to remind us, right? Polar bonds are talking about a small difference in that electronegativity value. But then I get to my my CH bond. And CH are even closer together in terms of electronegativity. And you may remember from a previous video that the CH is generally considered a non-polar covalent bond. They're so close in electronegativity that we don't see a large unequal sharing of electrons or anything like that. So CH bonds always are going to be non-polar. So I'll do that in purple. So non-polar, right, which means basically no difference in electronegativity, and we definitely include CHs in that. So that means this CH also is nonpolar. CC, those are the exact same element, so that's definitely no difference in electronegativity since they're the same element. Here's another CH, another CC, another CH, another CH, another CC. So I know that all those bonds are nonpolar bonds, so I do not need to put partial charges for those. Now, if I look at CCl, they do have a small difference in electronegativity. They're both on the same side, but they have a difference. So that's another polar bond. C and O, small difference in electronegativity. So I've got a polar bond here. There's a double bond there and a single bond. And OH, we just saw with water on the previous one, would also be polar. So I've got a lot of polar bonds here. Now, again, with the nonpolar ones, right, we don't have any charge. So there's no charge on a nonpolar because everything's sharing equally. But when you have a polar thing, you do have the partial charges. So I need to add the partial charges to this molecule. And to add the partial charges, right, that partial positive, partial negative, I look at every single individual bond and ask myself, which one's more electronegative? Whichever one is more electronegative gets the partial negative, because that's where the majority of the electron cloud is, the electron density. So between N and H, N is to the right of H, so that means the N is more electronegative, so that should be the partial negative. And that must mean that that H is partially positive. So I've added those dipoles, those partial charges, to that bond. Now I look at the next bond, I have another NH down here, same thing, partial positive on that H, I already got the partial negative on the N. My NC bond, which one's more electronegative? Nitrogen's to the right of carbon, so nitrogen's more electronegative again, which means it should have a partial negative, I already got that. But that means that this carbon should have a partial positive on it because it's in a bond with nitrogen, so I have a polar bond there. I skip all the CHs and the CCs, I don't put anything because of that, because they're nonpolar, but I do have a CCl bond. And between those two, the more electronegative one is the chlorine, because it's furthest to the right. So partial negative for chlorine, partial positive for carbon there. Go over here, I've got two CO bonds. C and O are both in that same row, that same period, but oxygen's more electronegative than carbon, so I know the little dipoles are going towards oxygen, so partial negative for the oxygen, positive for the carbon. Same thing for this one, partial negative for that oxygen. And then lastly, I have my OH bond. We already did that one on the previous example where the oxygen's more electronegative than hydrogen, so partial negative, partial positive for that. And I've got all of my partial charges on this molecule, on whatever this molecule is. So that's how we apply these, that's how we put these partial charges on here. And this will be a very important skill moving forward, because we're going to see a lot of compounds that are polar and a lot of compounds that are nonpolar. And these partial charges determine a lot, like their likely physical states, what their melting points and boiling points are they water soluble or not, all kinds of things. So this will be a really important skill, and I'll do more examples in the next video. But that's how we go about it. We got to find the partial charges, look at which atom in that bond is more electronegative, assign that one the partial negative, and assign the less electronegative atom partially positive. For those of you who do want to see the dipole arrows, which are not as common as seeing these partial positives, but I can draw the dipole arrows for you. Again, so the more electronegative oxygen has the arrow going towards it. Same thing here, same thing there, same thing here, same thing there, there, and there. So those would be all of the dipole arrows if you hear that language. So to sum up, right, we have these three different types of bonds that determine what type of compound that you are. And again, with the ionic compounds, right, we said that for these, there is a large difference in electronegativity. So from the far left, far right. However, for the polar covalent ones, we just had a small difference in electronegativity. So things that were on the same side of the periodic table, like we saw with all those nonmetals over there, carbon and oxygen, hydrogen and nitrogen, stuff like that. Versus the nonpolar covalent had basically no difference in electronegativity, right? Which again meant for us anything that was the same or CH bonds. And those differences in electronegativity caused a difference in how they share or transfer electrons, right? With ionic compounds, since they had a large difference in electronegativity, you saw a transfer of electrons from one atom to the other. For the polar covalent one, right, you ended up seeing a sharing of electrons, but it's not equal because one thing is more electronegative than another. So we saw an unequal sharing of electrons. And then for the nonpolar ones, since they had the same electronegativity, since there was no difference, we saw that equal sharing. That was like our fluorine, our F2. So an equal sharing of electrons. And then depending on what happened with those electrons, right, that gave us different things in terms of charges. So ionic compounds, since you actually gain or lose electrons, you have full charges on those particles. Right, like you'll see, I think I put like an Na plus or an Mg2 plus or a Cl minus or a O minus 2. You have like full on charges. Whereas with the polar covalent ones, we didn't have full charges because you didn't transfer a whole electron. It's just that the electron cloud shifted from one side to the other. And so you ended up getting those partial charges, the partial positive and partial negative. So partial charges. And then lastly, for non-polar covalent, since there was an equal sharing, we had no charges at all. So no charges on any of the atoms in those bonds. So that summarizes the differences between the ionic bonds, the polar covalent, and the nonpolar covalent. In the next video, we'll just do a bunch of examples, look at a whole bunch of different compounds, and decide what those compound structures look like if you combine those atoms. So look forward to that video. Take care.